Hi, welcome to Unacademy. Unacademy is the India's largest online learning platform. Now, it supports the GATE and engineering service students for their preparation. They are training these two courses from India's top educators. About myself, I G Venkata. I have total 16 plus years of teaching experience, and so far I mentored more than 60,000 students for their GATE examination. And at present I am pursuing PhD from JNTU Kakinada, and my specialization is VLSI design. Now, if Unacademy learning app is in your device, it's okay. Otherwise, follow this procedure to get the learning app, this app. Just go to Play Store. Type Unacademy on that, and click on this install button. Once click on this install button, you will get the Unacademy learning app. Now that one is going to install in your device. Okay, if you open that, then you will get what are the different courses available in that, and who are the top educators handling the courses of that. Now here just check the few of the top educators who are handling the classes. So Tiwari sir, Ankit Goyal sir, Jaspal Singh sir, Jain sir. See, he is an ex-IAS officer. He got All India top 1 rank in electrical engineering GATE twice, and he is a IIT topper. Okay. Now here few more top faculty. Now, so we are happy to announce that recently we started 2 batches for GATE 2023-1 and second batch for GATE 2022 for electronics and communication engineering students and for electrical students. Now there is a Ascend batch for GATE 2023 for electrical students. It is going to start from today, 1st of February 2021. Here are the few of the top faculty handling the GATE classes for this batch. Here are the top faculty. Okay, and please don't forget to use my code during subscription VRAW10 to get 10% discount. VRAW10. And here is another Ascend batch. This is also Ascend. Now for GATE 2023, this time it is for electronics and communication engineering ECE department. Okay, now this is also going to start from today. And Evolve batch for GATE 2022. Now this is for electrical engineering. Here are the top faculty who are handling the classes in this branch. So it is also going to start from 1st of February. And again Evolve batch for GATE 2022. Now this is for ECE students. It is also starting from today, February 1st. And next Evolve batch for GATE 2022. This time this is for civil engineering. Okay, just before I give it a Jaspal Singh sir, ex-IAS officer. Okay, now these are the top faculty who are handling the classes for civil engineering people. Okay, this is going to start from 25th of January. Already it was started. Now again Ascend batch for civil engineering for GATE 2023. It was started from 25th of January 2021. So don't forget to use my code VRAW10 during VRAW10 to get 10% discount. Okay, use this code during subscription, then you get 10% discount. Next one is a Evolve batch. This batch is for GATE 2022 chemical engineering. You must thank to Unacademy to provide this beautiful facility to you for chemical engineering students. At outside it is very difficult to get these classes for chemical engineering. You must thank to them. Now this batch also started from 25th of January 2021. Next, there is Evolve batch for mechanical engineering GATE 2022. Here are the top educators who are handling the GATE classes here, and this batch was started from 25th of January. Again, SN batch for GATE 2023, same mechanical department. This batch was also started from 25th of January. Okay, and don't forget to use my code VRAW10 during subscription to get 10% discount. Okay, by using this code you get 10% discount. Now, once again we check what are the different disciplines available in Unacademy for GATE and engineering service people. Now, mechanical engineering, electrical, civil, production and industrial, instrumentation, chemical, computer science and IT department, and electronics and communication engineering. These are the different courses available. Now, there are two subscriptions in Unacademy. First one is plus subscription. This plus subscription is the basic plan or basic subscription. Okay, and second one is iconic subscription. Second one is iconic subscription. Okay, now in iconic subscription it is the next level of the plan. In this plan you get the personal coach. For every student there is a personal coach. Personal coach is allotted to you. Okay, in both the subscriptions your classes are going to be taken care by the India's best educators, and live interactive classes are going there, and structured courses and PDFs they provide. Okay, and they conduct the live tests and quizzes. Okay, now the benefit of personal coach here is whatever the test or exam you written, that paper is going to be analyzed thoroughly, and they will prepare a report in that where you are strong and where you are doing mistakes, and in which subject and which topic you need more preparation. Okay, based on that they will prepare a study planner to you. Okay, now by following that study planner and the material what they prepared for you, for using these two, you can definitely success in your examinations. So the most important thing is the personal coach. He plays a vital role, okay, in your examinations. He guide you every time. More number of tests they will conduct. Okay, when they satisfy up to you are saying okay I am satisfied, up to that point they will conduct more number of tests. They will analyze every paper. Okay, they will give you the feedback of that, everything they give you. Okay, sometimes you are prepared, for example, even though you are preparing effectively, sometimes without proper coach, proper guidelines, okay, from the faculty, because of lack of guidelines, sometimes you may not success. Okay, but here personal coach is provided to you. For every student there is a personal coach. Okay, use this opportunity. Okay, now if you check the price for this, now for plus plan, the cost, it is available for 1 month subscription, 3 month subscription, 6 months, 12 months, 1.5 year and 2 year subscriptions. Okay, and the beauty here is they are providing EMI option also. Now sorry, by using this here, by using my code VRAW10 during subscription, you get 10% discount. Without discount it is a 30,250. After using my code VRAW10 during subscription, you get it only for 27,225. If you compare this amount, just 27,225, if you join somewhere for taking the classes, coaching for GATE, okay, 1 year you have to attend during holidays and public holidays, Saturdays and Sundays. Okay, throughout the year, the number of classes what you are attending, number of days you are attending, for that the transport charges, okay, and your lunch, breakfast, some snacks, okay, if you count all those, that cost, this is just more than that, hardly 3 to 4,000 more than that. Okay, just think once of it. Next, iconic plan, and if you check the iconic plan, Here, two subscriptions only. 1 year subscription, 1 year subscription and 24-month subscription, 2 year subscription. Okay, now after discount, after using my code VRAW10 during subscription, you get it by 10% discount. After discount, it is 45,225. 45,225. Okay, for 2 years it is 74,000. After discount, 66,600. Okay, now here personal coach they will allot to you. That is the main point, important point here. You need to be count. Okay, now this amount is more or less close to the amount what you are going to be paying at outside institutions. But the important thing is, at outside institutions you have to go there, you have to travel there, and you have to take the classes, attend the classes. But here the thing is different. You can sit at your home. Okay, faculty will teach the classes. Just take a note, take a class notes, and after that they will provide proper material to you. Okay, regularly they will conduct exams to you. So everything you can write by sitting at your home. And after completion of your exam paper, writing the exam, your paper is going to be analyzed from first point to last point. And your personal coach is going to guide you based on your analysis of your paper. They will prepare a proper study plan to you and they will guide. By following the instructions what they provided, definitely you will success in your examinations. Okay, don't waste your time. Okay, join today. Now I'm going to the problems sessions. Now already last session we done some problems. Okay, now see this problem. The intrinsic carrier concentration of silicon at 300 Kelvin is 1.5 into 10 power 10 per centimeter cube. Mobility of electrons mu n is 1500 centimeter square per volt to second, and mobility of holes is 450 centimeter square per volt to second. The silicon sample is doped with donors of Nd of 5 into 10 power 16 per centimeter cube, and then compensated by acceptor doping. See, after doping with Nd, it is compensated by acceptor doping. Compensated by acceptor doping. The compensated silicon sample has a resistivity of 1 ohm to centimeter. After compensation doping, okay, its resistivity is 1 ohm to centimeter. Determine the acceptor concentration, assuming that the mobilities remain unchanged. Assume that the mobilities remain unchanged. See, first I am going to writing the data what they given. See, Ni they given, mu n they given, mu p they given, and so sample is doped with the donor concentration. Nd they given 5 into 10 power 16 per centimeter cube. Okay, and then compensated by acceptor doping. After that it is compensated by acceptor doping. Now its a resistivity. After compensation, its resistivity is 1 ohm to centimeter. Then determine the acceptor concentration. Okay. Now, so whatever the Nd here you have, Nd here you have, Nd here we have, this is going to be electron concentration. So therefore your electron concentration under steady state is nothing but a Nd. It is 5 into 10 power 16 per centimeter cube. That is your N0 value. Okay, now I am going to calculating. This is doped with this much donor. Now I am calculating its resistivity. So resistivity of this one is 1 by conductivity. Once it is Nd and that too this Nd is greater than, much greater than Ni. So you can write it as its conductivity is N naught into Q into mu N. Okay. Now substitute the values. 1 by N naught is nothing but a ND into Q into mu N. Now it is 1 by ND is 5 into 10 power 16 into Q is 1.6 into 10 power minus 19 coulombs into electron mobility mu N they given, it is 1500 centimeter square per volt to second. Centimeter square per volt to second. After simplification I get, so it is 10 power minus 19, it is 16, 17, 18. Okay, it is 15 means it is 1.5 it became, we can write it as 3 by 2. Okay, now it is 0.8. Okay, now it is 4. So 1 by 12. So 1 by 12 ohm to centimeter. That is the conductivity. So now I am going to simplify this. So 1 by 12 divided by 12. So that is 0.083. 0.083 ohm to centimeter. This is the resistivity of a doped semiconductor ND. Okay, this is the initial one. First, with this donor density, this is the resistivity. Now after compensate doping, see, after compensate doping, they given its conductivity is a rho dash. Let us take our conductivity is resistivity is a rho dash. They given it as 1 ohm to centimeter. 1 ohm to centimeter. Okay. Now two conditions. After compensation, they given only its conductivity. They did not mention it is N type or P type. Okay. It's N type or P type depends on the comparison between Na and Nd. Okay, so you need to measure the amount of accept or impurity required for that. Now in that I am taking the case 1. First case I am taking, let Na is greater than Nd. Okay, Na is greater than Nd. In that case it behaves like a p-type semiconductor. It means it behaves like a p-type semiconductor, and in this case steady state hole concentration is Na minus Nd approximately. Now its conductivity can be written as, resistivity is written as 1 by conductivity, which is 1 by P naught into Q into mu P. They given it as 1 ohm to centimeter. Now from this I am getting the value of P naught equal to 1 by Q into mu P. Q value is 1.6 into 10 power minus 19 coulomb into mobility of holes. They given it as 450 mobility of holes, 450. Okay, now it is now 1.6 into 45, it is 72 divided by 72. It is 0.0138 into 10 power 18 per centimeter cube. Now I am writing it as a 1.38 into 10 power 16 per centimeter cube. This is the case. Now this is P naught, but P naught is nothing but a Na minus Nd. Therefore, Na minus Nd is this much. Now Na is this one plus Nd. So 1.38 into 10 power 16 plus Nd. Okay, just simplify that. So now it is 1.38 into 10 power 16 plus, so the Nd value they given, how much it is? So Nd given 5 into 10 power 16. 5 into 10 power 16. Now it is 6.38 into 10 power 16 per centimeter cube. This is the acceptor concentration. Okay, acceptor concentration. In case of Na is greater than Nd. For example, Na is less than Nd. Next case is, for example, Na is less than Nd. That means Nd is greater than Na. So at that time it behaves like N-type semiconductor. Steady state electron concentration is approximately Nd minus Na. Now they given its conductivity, its resistivity is 1 by conductivity, which is 1 by N naught into Q into mu n equals to 1 ohm to centimeter they given. Now from this we can write N naught equals to 1 by Q into mu n. So 1 by Q is 1.6 into 10 power minus 19, and mobility is they given 1500, I think so. For mu n they given it as 1500. Okay, now it is 2. 0.0416. 0.0416 into 10 power 17. 10 power 17. Okay, or it is 0.416 into 10 power 16 per centimeter cube. Our intention is to calculate acceptor concentration, what they are adding for what they compensate, amount added for compensation. So that is N naught. N naught is you are written as Nd minus Na. This is Nd minus Na. Okay, so from this I want Nd value, Na value. Take this Na this side, this one this side. Therefore Na equals to Nd minus 0.416 into 10 power 16. So Nd they given it as 5 into 10 power 16. So 5 minus 0.416. So it is 5 into 10 power 16 minus 0.416 into 10 power 16. So now it is 5 minus 0.416. 4.584. 4.584 into 10 power 16 per centimeter cube. That is the acceptor concentration. Okay, see here, see in GATE we have one problem, that is sometimes they will give options, two options in A, B, C, D. Sometimes they give answer is A and B. At that time you should be more careful. Here in this problem, see, this is your final answer. We have two answers here. You have finally two answers here. This is the one case. This is one case. Okay, if your semiconductor is after compensate doping, if you feel, if you consider your semiconductor is a p-type, this is the answer. Okay, if you are considering after after compensate doping also, it is a p-type n-type semiconductor, this is the value. Okay, so because they did not specify after compensate doping how it is working, they did not specify in this problem after compensate doping how it behaves, either n-type or p-type. Simply they given after compensate doping, its resistivity is 1 ohm to centimeter. Okay, so you can expect this level problem for 2 marks. So 2 marks in GATE examination is not that much easy. So you have to give high priority to this type of problems. Okay, thank you. Now I am going to moving to next problem. I think so you are understand this problem. Now see this problem. An intrinsic germanium sample, at room temperature has a resistivity of 0.50 ohm to centimeter. See this, sir, it is an intrinsic sample. That means intrinsic resistivity is 1 by conductivity. Intrinsic conductivity, which is 1 by Q into Ni into mu n plus mu p. We know that. Okay, the given this is 50 ohm to centimeter. Okay, leave it. Now the sample is uniformly doped to an extent of 16 to 10 power 13 arsenic atoms. Okay, arsenic atoms. So this is Nd. They given Nd. 6 into 10 power 13 per centimeter cube. Arsenic atoms per centimeter cube. And 10 power 14 boron atoms per centimeter cube. So boron is Na. 10 power 14 boron atoms per centimeter cube. Find the conduction current density. Current density if an electric field of 4 volt per centimeter is applied across the sample. And they given mu n and mu p. Okay, see, so the problem is they have a semiconductor. Initially it is intrinsic semiconductor, its resistivity is 50 ohm to centimeter. 50 ohm to centimeter. And after that it is doped with Nd and Na. After doping with Na and Nd, if you observe this, Na is greater than Nd here. Na is greater than Nd. Okay. That too, Na is 4 times greater than Nd. 4 times greater than Nd. Okay. Greater than Nd. And what you have to do is, you need to calculate the current density. First, you should know which type of current density, because we have two types of current densities: drift current density and diffusion current density. Here they are saying an external electric field of 4 volt. External electric field they are applying E, that is 4 volt per centimeter is applying to this. So the electric field is directed in this type. Now its value is 4 volt per centimeter. Now once external electric field is you are applying, now the current density is a drift current density. So due to this point, electric field, now I am going to concluding that the current density is drift current density. Therefore, we need to find drift current density. Drift current density. Okay, drift current density you need to calculate. Okay, now for this calculation of drift current density, you observed or not, NA is not that much greater than ND. NA is not that much greater than ND. Just a small value, only 4 times, not even 10 times. Previous comparisons, if you observe, it is a 10 power 4 times, 10 power 5 times, 10 power 5 times, 10 power 6 times more. But now it is not that much greater. But Na is greater. So due to this, from Na greater than this, you can conclude that it is a p-type semiconductor. It is a p-type semiconductor. Okay. Now this is acting as a p-type semiconductor. So once it is p-type semiconductor, drift current density J drift by p-type. J drift is, you can write under steady state condition, hole concentration P naught into Q into mu P into applied electric field E. So in this problem, they given Q value, mu P they given, and electric field also they given 4 volt per centimeter. So now the additional parameter you need to measure is P naught. Okay, if Na is much greater than Nd, then we can write Na is much greater than Nd. So we can write in that case steady state hole concentration is approximately Na minus Nd. But here this is not the case. It is not much greater. It is a little bit more. So at the time, by using a exact equation, you need to calculate P. So now steady state hole concentration is Na minus Nd by 2 plus square root of Na minus Nd by 2 whole square plus Ni square. Okay, Ni square. You observed one thing or not? In this problem, they did not give an Ni value. Okay, they did not give any Ni value. They did not give any Ni value. It is germanium. You can't take like silicon 1.5 into 10 power 10. For germanium, it is 2.5 into 10 power 8. But you can't take that value because to calculate that Ni value, they given a clue to you. Here is the clue they given. They know, you know the value of Q, mu n plus mu p they given, mu n and mu p they given. So from this you get the Ni value. Okay. So first calculate that Ni value and after that take that Ni and substitute there. Now from this I am calculating Ni value. So from this Ni is 1 by 50 into Q into mu n plus mu p. Mu n plus mu p. Now 1 by 50 into Q, 1.6 into 10 power minus 19 coulombs into mu n plus mu p. So it is 3800 plus 1800. 3800 plus 1800. Simplify this. So it is 5 into 16. You can write. Now see 2 zeros, it is 10 power 17. 10 power 17 by 5 into 16 into okay 56. Okay, now you can write that you get that value is 5 divided by 16 divided by 56. So that is 0.22 22 into 10 power 14 per centimeter cube. That is the Ni value you get. So now it is 2.2 into 10 power 14 per centimeter cube. That is the Ni value. Okay. Sorry, it is 13, 10 power 13, sir. Because it is 14, now it is 13. So 10 power 13 per centimeter cube. So that is Ni value. Now once you get the Ni value, just take that and substitute here. So Ni value is, we got 2.2 into 10 power 13 per centimeter cube. Now substitute the values in this equation of P per centimeter. Now equals to Na minus Nd. You need to get Na minus Nd. So Na minus Nd is, they given 10 power 14 and Nd is 6 into 10 power 13. So now it is 4 into 10 power 13 per centimeter cube. 4 into 10 power 13 per centimeter cube. Okay. Now, so it is 4 into 10 power 13 by 2 plus square root of 4 into 10 power 13 by 2 whole square plus Ni square. Ni is 2.2 into 10 power 13 whole square. Now it is 2 into 10 power 13 plus square root of, this is also 2 times, now 2 square is 4, 4 into 10 power 26 plus 2.2 into 2.2, 2.2 into 2.2, that is 4.84 into 10 power 26. Okay, now it is 2 into 10 power 13 plus, so square root of 4 plus 4.84, it is 8.84 into, just take 10 power 26 outside of the root, that is 10 power 13. Now I want square root of 8.84, square root of 8.84, that is 2.97. So now it is 2 into 10 power 13 plus 2.97 into 10 power 13, which is 4.97 into 10 power 13 per centimeter cube. That is the hole concentration, steady state hole concentration, okay, in that semiconductor. Now we need to measure drift current density. Just take the value and substitute in that. So we need to measure J drift, which is P naught into Q into mu P into applied electric field. Substitute the values. P naught 4.97. I am taking approximately 5, this one, for my easy calculation purpose, per centimeter cube. Okay. Now it is 5 into 10 power 13 into Q, 1.6 into 10 power minus 19, and mobility of holes they given 1800, and the applied electric field is 4 volt per centimeter. 4 volt per centimeter. Now just simplify this. So now it is, so 13, 14, 15, it is now 10 power minus 4, 10 power minus 4 into, so 5 into 1.6, 5 into 1.6 is 8, into 4 it is 32. Now it is 32, 32 into 18, 32 into 18, that is 576 into 576, it is 576. So that is you can write it as 57.6 milliamps per So drift current density amps per centimeter square. Okay, current per unit area, milliamps per centimeter square. This is the drift current density of that material. Previous problems we done directly we applied, but in this case the important point is you need to get the Ni value. Directly they given Ni value in previous problems, but in this case you need to get the Ni value from the knowledge of sigma I, intrinsic conductivity. From that knowledge you need to get the Ni value. Okay, and after that you substitute the values in that. Clear? So this is the problem. Now we are moving to next problem. Yeah, see this. Now this problem is calculate the fractional change in conductivity of an intrinsic semiconductor, assuming that the change in conductivity is only due to the variation in intrinsic carrier concentration. See this. Conductivity variation is only due to intrinsic carrier concentration. That means remaining all parameters are going to be constant. Okay, intrinsic carrier concentration with the temperature. See, fractional change in conductivity of an intrinsic semiconductor we need to get. So now, conductivity of intrinsic semiconductor is, we know that, Q into Ni into mu n plus mu p. And they given, assuming that the change in conductivity is only due to the variation of intrinsic carrier concentration with temperature. See, your Ni value is varying with respect to temperature. Okay, we know that. Okay, now you have to consider that. So now I am going to substituting Ni value. So what we know about Ni. Now we know the Ni value is, already we derived some constant A into T power 3 by 2 into E power minus Eg, energy gap, by 2 kT. This is the equation for Ni. Now I am taking this one and substituting here. Therefore intrinsic conductivity is Q into Ni value A into T power 3 by 2 into E power minus Eg by 2 kT into mu n plus mu p. Mu n plus mu p. In this, Q is constant, A is constant, and mu p, sorry, it is mu n, sir, mu n plus mu p. So it is mu n plus mu p. Okay, so all these are constants. This mu n plus mu p also constant. Now I am taking, let some constant k2 k dash I am introducing, or k, some constant k dash I am introducing. Let k dash is equals to q into a into mu n plus mu p. Okay, I am taking that one is a constant, which is constant. Now I am writing sigma I is some constant k dash into T power 3 by 2 into E power minus Eg by 2 kT. See this. Now variation of intrinsic with respect to temperature. That means your temperature is going to be a independent parameter, change, varying. Now I am going to be differentiating this with respect to okay, sorry, first take natural log on both sides. I am taking natural log on both sides. By taking natural log on both sides, so ln of sigma I is ln of these things. Now ln of k dash into t power 3 by 2 into e power minus eg by 2 kt. Now ln of sigma I is ln of k dash into t power 3 by 2 into this one is ln of k dash plus ln of t power 3 by 2 plus ln of e power minus eg by 2 kt. Okay, now here this 2 gets cancelled, so ln of e power something is that one. Now you get finally ln of sigma I is ln of k dash plus 3 by 2 into ln of t minus energy gap by 2 kt. Now I am differentiating both sides with respect to t. Now differentiating on both sides. On both sides. So now it is differentiation of ln of sigma I is 1 by sigma I into d sigma I by dt, because with respect to temperature we are doing, is equals to differentiation of ln of this, so it is constant, this is constant, that's why differentiation of that one is 0 plus 3 by 2 into, so its differentiation is 1 by t into 1, and here it is minus eg by 2k into 1 by t, differentiation is minus 1 by t square. Okay, minus 1 by t square. So it is minus into minus, it became a positive. Now we can write 3 by 2 into 1 by t plus eg by 2k t square. So we can write simply, now simplifying this, now this is a d sigma I by sigma I into 1 by dt equals to, I am taking 1 by t common, into 3 by 2 plus energy gap by 2k. Okay, now so this is the final equation. Now I am going to normalizing this expression to a for a semiconductor. Now instead of sigma I am taking sigma. Okay, therefore, so you can write, this is the expression finally. Now we can write d sigma by sigma equals to, taking this dt this side, dt by t into 3 by 2 plus eg by 2k. So another t square it is, so taking 1t common, now another t is there, 2kt. This is the final expression, fractional change. Okay, see, change in conductivity is d sigma, fractional change in conductivity is d sigma by sigma. Okay, so this is the equation, dt by t into 3 by 2 plus eg by 2 kt. Okay, next one. Now how can we use that equation? Now we check that one in this problem. The conductivity of an intrinsic silicon sample at 300 Kelvin is this much, 4.4 into 10 power minus 4 ohm to centimeter inverse. Determine the conductivity of the semiconductor if temperature rises to this one. So our equation is d sigma by sigma, we derived it as dt by t into 3 by 2 plus eg by 2 kt, we derived this. Okay, now just I am going to getting d sigma. Okay, so what now, from this we can write d sigma equals to sigma into dt by t into 3 by 2 plus energy gap by 2 kt. Now the required sigma conductivity is whatever the regular conductivity plus small change in conductivity, not small change in conductivity. because you are increasing temperature. Once increasing temperature, new charge carriers are generated. Once new charge carriers are generated, more conductivity you get. So you need to get sigma plus d sigma. First I am getting d sigma from this. Now here dt and t is there. Now T is 300 Kelvin. Okay, dt is 315 minus 300. So that is 15 Kelvin. That is the dt value. That is the dt value. Now I am taking this value and substituting here. So d sigma is sigma into dt is 15 by t is 300 into 3 by 2 plus, we know the energy gap at T 300 Kelvin, it is 1.1 electron volt by 2 kT. 2 into kT value 0.025 electron volts. Just simplify this. Now sigma into, so it is once it is 20, 1 by 20, 0.05 into 3 by 2, 1.5 plus, so 1.1 by, now I am doing that calculation. So it is 1.1 divided by 2 divided by 0.025. So that is 22. Now it is 22. So now total it is 23.5 into 0.05. 23.5 into 0.025. 0.587. So it is 0.587 sigma. That is the d sigma. Okay, but we need sigma dash after increasing temperature. Now sigma dash is sigma plus d sigma. So sigma plus d sigma is 0.587 sigma. So now you can write it as 1.587 sigma. So 1.587 into, they given already sigma value to you. Sigma is 4.4 into 10 power minus 4. 4.4 into 10 power minus 4. 10 power minus 4. Just multiply this. So 4.4 into 1.587. So it is 6.9 into 10 power minus 4 ohm to centimeter inverse. This is the total conductivity. Change in conductivity is 0.587. Okay, that is the change in conductivity. Okay, now next we are moving to another problem. See, the resistivity rho V, rho naught of germanium sample is measured at 300 Kelvin. The sample is then remelted. That means remelted means heated and doped with 4.4 into 10 power 16 arsenic atoms per centimeter cube. The new crystal resistivity of 0.1 ohm to centimeter, okay, and is n-type semiconductor, See, the new crystal is a n-type semiconductor. Determine the type and concentration of impurity atoms in the original sample. In the original sample, what are the impurity atoms present and type of original sample, original material. Okay, and value of rho V. Assume mu n equals to 2 times mu p. Okay, that is 3000 centimeter square per volt to second. Okay, just once think of this problem. They take an initial semiconductor, okay, and at 300 Kelvin. After that, that is remelted. Remelted means heated. So it is melted high. After that, doped with 4.4 into 10 power 16 arsenic atoms. Now, here I have only one clear picture, one clear point. First, I am starting that point. First, it is doped clearly. After doping, its resistivity is 0.1 ohm to centimeter, 0.1 ohm to centimeter, and it is n-type. So now, first I am going to that. After doping, its value, its resistivity is sigma n, because it is n-type, clearly they mention, which is 1 by rho n is 1 by sigma n, which is 1 by amount of doping, doped with arsenic atoms. Okay, amount of doping. See, sorry, not this. The new crystal they mentioned. So amount of doping is, so it is n-type. That's why under steady state electron concentration is n naught into q into mu n equals to, they given it as 0.1 ohm to centimeter. Okay, the new crystal after remelted and after adding this, it is a new crystal, and that new crystal is a n-type material. So for that they given conductivity, resistivity. Now that resistivity is 1 by conductivity. So 1 by n naught into q into mu n. N naught is the under steady state electron concentration. So now it is 0.1 ohm to centimeter they given. Now they given mu n also to me. Now substituting values, from this I calculate the n naught value. Now n naught is 1 by q into mu n into 0.1. So which is 1 by q, 1.6 into 10 power minus 19 coulombs, into mu n they given, mu n is 3000 into 0.1. Okay, so now its value is, so divided by 1.6 divided by 3, it is 0.208 into 10 power 17 per centimeter cube. So you can take it as approximately. So therefore n value is, n naught value is approximately 2 into 10 power 17 per centimeter cube. This is the approximate n value after remelting and adding doping. Okay, now see this, what is the amount of what type of impurity they are adding? They are adding arsenic atom. So Nd they are adding. Okay, and it is remelted. Okay, so it is Nd, fine. Just a minute. So far we get the n naught value. That means after done everything, okay, after done complete thing, your material, in that material electron concentration is 2 into 10 power 17. Okay, and they added Nd. What the Md they given? They given Nd value 4.4 into 10 power 16. So 4.4 into 10 power 16 per centimeter cube. Okay, now here I am going to applying charge neutrality. So now here I have a semiconductor like this. In this you added Nd 4.4 into 10 power 16 per centimeter cube, and under steady state electron concentration is 2 into 10 power 17 per centimeter cube. Okay, and it should also maintain some. So once electrons are there, automatically holes also is there. Under steady state, what is the hole concentration? And they did not specify anything about Na. Okay, they did not specify anything about Na. Now you need to get that Na value. How much they are adding? Okay, see, compared to Nd, this is more. Okay, so you need to get that Nd value. Now from this, electron concentration is N naught. Sorry, already we use N naught. Okay, this N naught and this N naught both are same. Okay, just a minute, sir. Okay, see, this Nd is more than this N naught. Okay, that means, sorry, N naught is we get more value. Not more value, no chance. Just a minute. So 0.2. Sorry, sir, it is a 0.208 10 power 17. So 2 into 10 power 16. 10 power 16. Sorry, per centimeter. Now, see, Nd is more than N naught. Nd is more than N naught. Okay, so once Nd is greater than N naught. Okay, Nd is greater than N naught in this sense. The net electron concentration is, okay, whatever the doping you added Nd minus initially acceptor concentration what it has. Okay, initially whatever the acceptor concentration there we have, that is net doping. See, after remelting and adding something, finally it shows n-type material, so electron concentration is that much. Okay, that means it is going to be added with some other material, that is acceptor impurity. Now N naught is Nd minus Na. Now you know the N naught value and Nd value, take those two, substitute here, you get the Na. From that Na is Nd minus N naught. By subtracting N naught from this Nd, it is 2.4 into 10 power 16 per centimeter cube. So initially the amount of doping is acceptor doping in that, and its value is 2.4 into 10 power 16 per centimeter cube. Initial this is. Therefore, the material is, the initial material is, the initial material is p-type, because here we got Na value, it is p-type. Okay, and its conductivity they want, sigma naught they want, resistivity they want. So resistivity means 1 by sigma naught. Okay, so it is a 1 by Na into Q into mu p. So 1 by Na value 2.4 into 10 power 16 into Q 1.6 into 10 power minus 19, 10 power minus 19 into mu p. They given mu n equals to mu p equals to 3000. Now mu p is 1500. 1500. Okay, so no need of p naught here, just this is sufficient. Okay, even you are applying also you get the same. Now just simplify this. So it is sorry, 10 power minus 19 it is. So minus 19 it is 16, 17, 18. So 10 power minus 1. So it is a 3.2, 1.5. Now it is 0.8. Okay. So it is 2.4. So 1 by 2.4 into 2.4. 1 by 2.4 divided by 2.4. That is 0.173. 0.173 resistivity ohm to centimeter. Okay, that is the resistivity of the material. So initial semiconductor is a p-type semiconductor and its resistivity is 0.173 ohm to centimeter. Okay, next. Okay sir, we'll wind up today. Tomorrow we go to the, okay, today we go to another one. So another problem is the important problem, not this. Yeah, just see this problem. In the figure, ln of rho I is plotted as a function of 1 by t. See, this is the plot between ln of sigma I, resistivity of intrinsic, with 1 by t, plotted as a function of 1 by t, where sigma I is the, sorry, rho I is the intrinsic resistivity of silicon, t is the temperature, and the plot is almost linear. The plot is almost linear. Okay, so this is almost linear, sir. The slope line can be used to determine, so whatever the slope of this line is used to determine or used to estimate which option, which one, energy gap or sum of mobilities mu n plus mu p, or reciprocal of sum of electron and hole mobilities mu n plus mu p whole power minus 1, or intrinsic carrier concentration. Okay, see, first I am taking the sigma I. Rho I is 1 by sigma I, we know that. So now it is 1 by sigma I is Ni into Q into mu n plus mu p. Mu n plus mu p. Okay. Now, and at the same time we know the Ni value. We know Ni value. That is some constant A into T power 3 by 2 into e power minus Eg by 2 kt. That is the value of Ni. Just take this one, substitute here. Now rho I is 1 by Ni, means A into T power 3 by 2 into e power minus Eg by 2 kt into Q into mu n plus mu p. Okay. Okay, sir. Now, in this, it is constant. It is constant. It is a function of temperature, because your temperature is not constant here. It is varying as a plot. It is varying. It is variable. Varying. And once temperature is varying, it is also going to vary. And at the same time, the mobilities of electrons and holes are varying. Okay. Now, the material is operating not at extreme temperature. Okay. It is operating just more than room temperature. Just, you can assume. Now, in that case, you can take mobility of electrons directly proportional to T power minus 3 by 2. Already we discussed about this one, effect of temperature on mobilities. Okay, and you can write this one is mu n equals to a constant value of electron on the steady state, mu n naught, into a constant T power minus 3 by 2. Similarly, I am writing mu p is mu p naught into T power minus 3 by 2. Okay. Now take this mu n and mu p, substitute here. Therefore rho I is 1 by a into t power 3 by 2 into e power minus eg by 2kt into q into mu n plus mu p. So mu n is this much, mu p is this much. By taking 3 power 3 by 2 common, e power minus 3 by 2 common, so you can write it as mu n naught plus mu p naught. Under steady state, that means at a constant temperature the values. Now here this one gets cancelled. Okay, and this is a constant, it is a constant, it is a constant, and it is constant, it is also a constant. So 1 by some constant is again a constant. Now I am representing this one by sigma I is some constant. Okay, some constant C I am assuming. Some constant C into e power. Now I am taking this one into numerator. E power Eg by 2kt. Eg by 2kt. Where C equals to a constant, where C is constant, and its value is here we are taking 1 by a into q into mu n naught plus mu p naught. Okay, now in this I am taking natural log on both sides. By taking natural log on both sides, you can write ln of rho I is equals to ln of constant into e power eg by 2kt. So now ln of is written as ln of c plus ln of this one. So ln of this one is nothing but a eg by 2kt. So from this, finally I am writing ln of sigma I equals to k eg by 2k into 1 by t plus ln of constant. Now it is in the form of, on y-axis in our plot, it is a plot between 1 by t and ln of sigma I, so rho I. Now on y-axis you have this one, on x-axis 1 by t. Now this is some constant. So now it is the slope. Y is equal to mx plus c. It is a straight line. And in the clearly in that they given the plot between 1 by t and sigma ln of sigma I, ln of rho I is approximately linear. So linear means a straight line. Okay. Now the slope of that one is Eg by 2k. Slope of that one is Eg by 2k. Now the slope is Eg by 2k. Eg is energy gap, k is Boltzmann constant. Okay. Now what they want here, just we calculated slope. In options also they ask that one. The slope line can be used to estimate. So by using the slope of that, you are going to estimating the energy gap, because k is constant here. K is constant. So slope they given something, then from that you can estimate its energy gap. So it is used to estimate the band gap energy of silicon. Energy band of a silicon or energy gap. Okay, so this is a nice problem, sir. Try to practice this type of problems, not like see, don't go for regular problems taking the values, substituting the equations. Initially we done those things only. Okay, so to get some command on the subject, initially you need to do that, and once you got command, now try to solve some different model problems. Okay, Now, thank you very much. Thanks for spending your valuable time with me. So, remaining problems we discuss in the next session. Please don't forget to use my code VRAW10 during subscription. Okay, by using this code during subscription, you get 10% discount. And click on this bell icon for notifications. Okay, and join our Telegram group to get the latest updates on upcoming videos. And don't forget to subscribe and give your valuable comments on YouTube. Okay, to strengthen ourselves and to give a good quality data to upcoming students. Okay, thank you very much, and thanks for spending your valuable time with us. Follow these videos and let's crack the gate. Thank you very much.